Hypothesis testing with the normal distribution. In this section, we will be dealing with the situation where samples are drawn from a normal distribution. It is true that when n is sufficiently large, sample means are normally distributed irrespective of the underlying distribution. So what I mean by that is that we can take samples from a binomial or an exponential distribution, and if we just look at the distribution of the means of the samples, they are normally distributed. This is known as the central limit theorem. However, as mentioned above, here our original distribution will also be normal. We can test a hypothesis about the mean of a normally distributed random variable by looking at the mean of a sample taken from the whole population. Suppose the whole population is normally distributed. Sample means for samples of size n drawn from this distribution are distributed thus. You can see that x bar denotes the mean. You can see that the mean is the same, it's mu, but the variance is now sigma squared over n as opposed to sigma squared. We can use the distribution of sample means to determine whether the mean from one particular sample is statistically significant. We'll see this in some examples coming up. We have met the idea of hypothesis testing and critical regions before. So this might be a critical region here, which means this will be the acceptance region. If the mean of our sample lies in the critical region, we would have evidence at the level of the test to reject the null hypothesis. You should remember from earlier work that the null hypothesis is normally a situation of no change. There is an alternative hypothesis, the form of which will determine the type of test we perform. So let's just remind ourselves of that. The null hypothesis here might be something like the mean is 20, and that would normally be because we know the mean to be 20 at the moment, and some situation has changed, and we want to see if it's different, but we assume it's the same as it has been. The alternative here might be that the mean has increased. This would lead to a one-tailed test with the critical region at the right-hand end, like the one shown here. So if we get a result in the critical region, that would make us think that the mean has actually increased. We might have the same null hypothesis, but that the mean has just changed and we don't know whether it's changed up or down. This would lead to a two-tailed test where the critical region would be distributed at either end. An example would be a 5% test would give us 5% as this area here, or 0.05 as the area here on a one-tailed test, and 0.25 at either end, giving us a 5% test with a two-tail.